Hello, I'm Rex, and today I'm presenting the causal conditions analyzing and improving optimal transport for conditional flow-based generation. We are interested in the problem of conditional flow-based generative modeling. Concretely, we wish to obtain samples x of 1 from a target distribution Q of x1 given C under some condition C. In the illustration on the right, the target distribution is a top distribution which is a mixture of two Gaussians, and the condition is either C equals to 0 or C equals to 1 as indicated by their colors. During both training and testing, we would have access to a source distribution Q of x0, which is shown as the bottom distribution. During training, we randomly sample pairs of x0 and x1 and we compute the flow matching loss. During testing, we first sample from Q of x0 and then we numerically integrate those samples from x0 to x1 following the learned flows. Note that straighter paths in the flow would lead to a more efficient numeric integration and therefore faster sampling. In the illustration on the right, note that the paths are not straight, because the paths overlap during training. To improve the efficiency of inference, mini-batch optimal transport or OT was proposed to straighten the paths in the unconditional setting. Mini-batch optimal transport changes the pairings during training from random pairings to be an optimal transport mapping. This can straighten the paths during testing, leading to more efficient inference. However, in the conditional setting, this skews the prior. Specifically, we are now sampling from Q of x0 given C. However, we have no access to Q of x0 given C during testing. Instead, we can only sample from Q of x0. This mismatch between training and testing leads to a degradation in the obtained samples, as shown in the illustration on the right. As we can see, the samples that we obtained do not match the target distribution. To address this issue, we propose conditional optimal transport flow matching or C2OT. Our goal is twofold. First, we want to fix the prior skew of optimal transport. At the same time, we want to maintain the straight path as induced by optimal transport to obtain efficient inference. To do this, we add a conditional aware waiting term to the optimal transport cost function. The intuition is that this penalizes transport between samples that have different conditions. As shown in the illustration on the right, C2OT can generate high-quality samples without degradations, while maintaining the straight paths. C2OT works for both the discrete and continuous conditions. In this illustration, we experiment with the 8 Gaussians to Moon's dataset. The source distribution is the mixture of 8 Gaussians, and the target distribution consists of 2 half-moons. On the left, we show the case with discrete condition. That is, the condition is either 0 or 1, indicating which of the half-moons does the sample belong to. On the right, we show the case with continuous condition, where the condition is the x-coordinate of the target sample. On the first row, we show the result of single-step inference, which relies on having straight paths for high-quality samples. On the second row, we show the result of using adaptive many-step inference, which is the more expensive step. Note that C2OT have notably better performance with both types of conditions. Baseline flow matching fails to produce reliable results with a single step because the paths are too curved. Optimal transport methods performs poor quality samples in both the single step and the many step samples because of the aforementioned prior skew. We have conducted more experiments in the paper on the CIFAR10 and ImageNet datasets. Please refer to the paper for more details. Our code is also available online. Thank you.